Welcome back to another video in this series where I'm summarizing and providing code examples for the popular book Reinforcement Learning by Richard Sutton and Andrew Barto. In the previous video, I covered the multi-arm bandits problem, which serves as a partial version of the full RL problem. In this video, we'll learn about the full RL problem and how it's formalized as a finite Markov decision process. Markov decision processes, or MDPs, have actions and rewards that we're already familiar with from the multi-arm bandits problem. They also have the associative aspect discussed in at the end of the last video. There's also one more important addition, which is the concept of states. In MDPs, actions that the agent takes do not just determine reward, but also influence the next state that the agent enters. In the bandit problem, the goal was to learn Q star, or the optimal action. And in an MDP, the goal is to learn either Q star SA, which is the optimal action given the current state, or V star S, which is the optimal state given that actions are selected optimally. Basically, MDP is just an abstraction of the problem of goal-directed learning from interaction. It states that any problem of learning goal-directed behavior can be reduced to three signals that get passed between the agent and the environment. One signal to represent the choices made by the agent, which is in this case the actions, and one to represent the basis on which the choices are made, in this case the states, and one to define the agent's goal, which is in this case the rewards. The reason that MDPs are used to represent problems in reinforcement learning is that they're so flexible. For example, the timestamps don't have to correspond to real time. They can be arbitrary. The actions could be low level, for example, controlling the velocity on robot motors, or high level, for example, controlling general direction of movement for a robot arm. So they can be applied to a variety of tasks. States can be anything that might be useful in helping the agent make decisions. When representing a problem as an MDP, how the states, actions, and rewards are chosen can have a big impact on performance, and choosing them wisely is more of an art than a science. An MDP can be visually represented through the agent-environment interface. In this interface, an agent takes an action at time step t in the environment, and in the next time step, it receives a reward and a new state. The set of all states, actions, and rewards can be represented as S, A, and R, and a trajectory is a sequential list of states, actions, and rewards that occur in the environment. For example, being at state S0, taking action A0, and at the next time step, receiving a reward R of 1, and then repeating so on and so forth. The dynamics of an environment, which are also known as the transition probabilities, determine the likelihood of ending up in some new state and getting some reward if an agent was to take some action from the current state. This can be read as P is equal to the probability of ending up in some new state S prime and receiving some reward R, given that the current state is S and the action taken is A. In deterministic environments, taking the same action from the same state will always put you in the same new state with the corresponding reward. The reason that we use transition probabilities is because in stochastic environments, you could take the same action from the same state multiple times and end up in a different subsequent state each time with some different probability. The reward hypothesis states that all goals can be simply thought of as the maximization of the expected value of the cumulative sum of reward. This use of reward signal is a distinctive feature of reinforcement learning as opposed to other learning methods. When choosing what reward should be, we have to be careful not to input knowledge about how we want the agent to achieve the goal, but rather what we want it to achieve. For example, in chess, you could give rewards to an agent for taking pieces as a means of winning the game. The problem with this is that an agent could learn to simply take pieces at the expense of winning the game. So instead, a reward should be given for the actual goal, which is winning. We now understand that the goal of an MDP is simply to maximize the expected reward or return. And the simplest definition of expected return is just a sum of all rewards, represented by this formula G of t, which is equal to R of t plus 1 plus R of t plus 2 plus R of t plus 3, all to R at the final time step t. And this formula works for tasks that are episodic, meaning they have a clear and represented final timestamp, after which the environment resets. The problem with this formula is that it does not work for tasks that are non-episodic or continuous, which are tasks that have no clear end. In these tasks, the final timestamp t can be equal to infinity, so what we're trying to maximize is infinite. For continuous tasks, we define expected return using this concept of discounting, which allows the agent to maximize the sum of discounted rewards. So as you can see in the formula, we add this value gamma, which is known as the discount rate or discount factor. Gamma is a parameter between 0 and 1 that determines the present value of future rewards. It causes the previously infinite sum to have a finite value, so we can now calculate expected return for continuous tasks. As gamma increases, future rewards are prioritized, and as it decreases, vice versa. If gamma is equal to 0, then the agent only cares about maximizing the immediate reward. To solve an MDP, an agent uses policies and value functions. A policy is a map from states to the probability of selecting actions from each state. Pi A of S is the probability that A of T is given that that A of T is taken under the policy given that S or T is the current state, or the likelihood of selecting action A from state S under the policy pi. So value functions estimate how good it is to be in a particular state or to take a particular action from a given state. This is a special equation, this Bellman equation for V pi, and it's known as the Bellman equation for a state value function, with defined with respect to the policy pi. So it can be read as the value of any state is equal to the discounted value of the possible next states plus the reward expected along the way, all weighted by the probability of those next states occurring. So similar to the state value function, we can also use an action value function Q, which returns the value of taking a particular action from a given state, instead of just the value of that state itself. For any Markov decision process, there is at least one optimal policy, if not more, that determines the best behavior. The way the agent achieves its goal of maximizing expected return is to learn the optimal policy. All the optimal policies share two things, the first of which can be seen here, which is the optimal state value function, V pi. So similar to the Bellman equation for state value functions we just saw, it's very similar, and it looks complex, but it can be simply understood on the last line as the value of a state under an optimal policy must be equal to the expected return of the best action from that state. The other thing all the optimal policies share is the optimal value function Q star, which can be understood as the value of a state action pair under the optimal policy is equal to the expected return of the best action. So they're pretty much saying the same thing. If we can solve the Bellman equations for V star and Q star, then we can solve a given MDP, since we will have the optimal policy. You could think of solving these equations as doing an exhaustive search across the MDP of all the possible states you could end up in, and of all the possible actions you could take in getting their value. As you can probably imagine, this works in theory, but usually doesn't work in practice for three reasons. Firstly, we would need to know accurately the dynamics of the environment, but this is often unknown. Secondly, we need to have enough computation space and resources. For a game like backgammon, there are 10 to the 20 states, which is more than any of today's modern computers could handle. So it's usually impractical. And thirdly, the problem must follow the Markov property, which means that the current state of the process is enough to predict the future states. Since usually at least one of these conditions is not applicable, we cannot directly solve for V star and Q star, usually, but instead the agent learns to approximate them through experience. So in this video, we covered lots of things from MDPs, the agent environment interface, environment dynamics, the reward hypothesis, expected discounted return, and introduced policies and value functions and how those are used to solve MDPs. In the next video, we'll look at our first set of solutions to MDPs, which are dynamic programming solutions. Thanks.